Hello, this is Dr. Hanaa Assil, and these are questions and answers on transition metals. So this is basically for Unit 5 of the A2 Chemistry Edexcel. So let us take a look at some questions and discuss the answers. This first question says, which of these is a D block element but is not a transition element? Now, remember which ones are D block elements. They are the ones in this area of the periodic table in which the electron configuration ends with electrons in the D sublevel. But not all the D block elements are regarded as a transition element, because the definition for a transition element is a D block element that forms one or more stable ions with incomplete d orbitals. So a transition element must have incomplete d orbitals in the ions. The stable ions should have incomplete d orbitals. So let us take a look at cobalt. If you look at cobalt, cobalt has 27 electrons, so its electron configuration will end in 4s2 3d7. Now when this cobalt forms an ion 2+, you have to remember, when we form ions in transition elements, we remove the electrons from the 4s first. So if I'm trying to write the electron configuration for cobalt 2+, then we're going to remove the 2 electrons from the 4s. So we still have the 3d incomplete. Remember, the 3d has 5 orbitals. To be complete, they must have 10 electrons. So if it has only 7, this is incomplete d orbitals. So cobalt is regarded as a transition element. What about copper? Copper is 29, atomic number 29. And remember that we said, usually when we distribute electrons, we should fill the 4s first before the 3d. But the copper is an exception, because if we say 4s2 3d9, that is not very stable, because the 3d needs only one more electron to be filled. So we don't say 4s2 3d9, we say 4s1 3d10. That it means the 4s is half filled, that is still stable. The 3d now is completely filled, and that is stable. So this is the electron configuration for copper. Now, when copper forms ions, like copper 2+, we said we remove electrons from the 4s, and then we go on to the 3d and remove electrons. So if I want to remove 2 electrons, then I'm going to remove the electron in the 4s, 1 from the 3d, so the 3d is incomplete. So copper is a transition element. What about nickel? Nickel is 28, 4s2 3d8. If it forms nickel 2+, then we remove the electrons in the 4s. The 3d is still incomplete, so nickel is transition. What about zinc? Zinc has 30 electrons. That means 4s2 3d10. And its stable ion is zinc 2+, but that means I just remove the electrons from the 4s. And the 3d is still complete. So zinc is not regarded as a transition element. This question again says the element zinc is not classified as transition metal. Why? Again, we said zinc is not transition because its stable ion 2+ still has a filled 3d sublevel. So this is not transition. Nickel is classified as transition. Why? Because nickel is 28, so this is the electron distribution. You're going to form nickel 2+. It forms stable ions with partially filled d orbitals. Are we okay with all of that? What about mercury? It's saying this is the distribution for mercury. Now mercury has +1 or +2. Explain why mercury is classified as D block but not transition. Again, this is the configuration for mercury +1. This is the configuration for mercury +2. So we're removing the 2 electrons from the 6s. I still have a filled 5d. So it is D block because it has electrons in the d orbital. The last electrons are in the d orbital. It's not transition because its ions do not have incomplete d orbitals. Some of the properties of manganese depend on electronic configuration. Complete the electron configuration for manganese atom and manganese 2 ion. Okay, so how do you remember how we put the electron configuration? First of all, we look at the periodic table. Manganese has atomic number 25, and that means argon, which is 18, and I'm left with 4s2 3d 5. That is the atom. When we form 2+ ion, again, when we form the 2+ ion, we remove the electrons from the 4s first, so I am left with this electron in boxes notation. What is the electronic configuration of ion 2? Well, ion 2, again, iron has atomic number 26, and that means I should have 4s2 3d6, but I want to form 2+. That means I removed the electrons that were in the 4s, and I'm left with only the 3d6. Which of these has the greatest number of unpaired electrons in each of its atoms? You should be able to draw the electron configuration. So chromium is 24, so it's 4s1 3d5. Again, this is the other exception to the rule of filling 4s before 3d, because this is 24, so it should be 4s2 3d4, but then we said 3d4 needs only one more electron to be filled, so we make it 4s1 3d5 so that they're all half filled and stable. So this is the electron configuration of chromium. What about iron? Iron is 26, so 4s2 3d6. Manganese, 4s2 3d5. Vanadium, 4s2 3d3. Again, I'm going to remind you, we put 1, 1, 1 into each orbital in the 3d, and then we start pairing. So the one that has the greatest number of unpaired electrons among these is chromium. Electronic configuration of atoms of an element is this. What is the maximum oxidation number shown in compounds of this element? If we have any of the transition elements we're going to talk about, what is the maximum oxidation number? Remember, transition elements have more than one oxidation state, and the maximum is if we remove all the electrons in the 4s and the 3d. So for this element, we have 6 electrons that we can remove. So the oxidation number, the maximum oxidation number this element could have is +6. What's a ligand? Remember, a ligand is a species that can donate a lone pair of electrons and form a dative bond, or what we call a coordinate bond, to the central metal ion. So first of all, a ligand must have a lone pair of electrons to donate. So it is something that has a lone pair of electrons, and it can donate it to make a dative bond. What kind of ligands do we have? You should know that we have monodentate ligands, bidentate ligands, and polydentate ligands. So a ligand is something that has extra lone pair of electrons. So cyanide, C triple bond N, is a ligand. It has a lone pair of electrons that it can use to form a dative bond to the central ion, metal ion. Chlorine is also something that has lone pair of electrons, the chloride ion. has a lone pair of electrons, so this is Cl minus actually, and it uses one of the lone pair of electrons to form a dative bond to the central atom. If the ligand forms only one dative bond to the central atom, it is called monodentate. So the cyanide is monodentate, chloride, water, hydroxide, each of these are monodentate ligands because they can form one dative bond to the central metal ion. Now, some ligands can form two. So bidentate ligands can form two dative bonds to the central atom. So these are things that have on their ends O minus or N that have lone pair of electrons that can be used to make a dative bond. A polydentate ligand is one that can form several dative bonds to the central atom. So that polydentate ligand is called EDTA. EDTA can form 6 bonds, 6 dative bonds to the central atom. So we say it is hexadentate or polydentate. So this question says, which complex contains only monodentate ligands? Which of these were monodentate? Cyanide is a monodentate because the cyanide group, C triple bond N with a negative charge on it, this forms one dative bond to the central atom. So this is actually the one that can form only monodentate. This is the only monodentate ligand. The C2O4, this is an oxalate ion, and we said these are bidentate. Each oxalate C2O4 will form 2 dative bonds to the central metal ion. This is EDTA. EDTA we said is hexadentate, and it forms 6 dative bonds with the central metal ion. And this one is called 1,2-ethane diamine. This is ethane with an amine group on each carbon. So each of the amine groups can form a dative bond with the central atom. So this is bidentate. So the one that has only monodentate ligands is that first one. Copper 2 ions form a complex with 1,2-diaminoethane, which is written like this, and that means that the copper makes 3 bonds or dative bonds with 3 of these molecules, diaminoethane. What type of ligand is 1,2-diaminoethane? That's this one. This is the 1,2-diaminoethane. So we said this type of ligand is bidentate. We have 2 nitrogen atoms on both ends, so each of them has lone pair of electrons that can form a dative bond. So this is bidentate. What is the coordination number when copper forms dative bonds with 3 of these? What do we mean by coordination number? Coordination number means the total number of dative bonds made by the central metal ion. So how many dative bonds go to the central metal ion? Well, this, of course, these are 6 dative bonds. So we say the coordination number is 6. What is the coordination number of chromium in this complex ion? Again, what do we mean by coordination number? It's the total number of dative bonds that are formed with the central metal ion. So the total bonds here are 6 dative bonds made to chromium. The structure of the complex is shown. What is the coordination number of chromium here? Remember, coordination number means the number of dative bonds formed to one central atom. So the one central chromium is forming how many dative bonds here? Each of the chromium is forming 6. So the coordination number of the chromium in this complex is 6. A complex ion of chromium 3 has this formula. where X is the overall charge. What is the coordination number of chromium in this complex? Again, if we draw it, we have chromium going to 2 chlorines and 2 of this molecule, which we called 1,2-diaminoethane or ethane diamine. Now, this, what is the coordination number here? We said the total number of dative bonds made to the chromium. Well, it has 6 dative bonds attached to it. What is the overall charge? How do we calculate the overall charge of a complex? Now, he's telling me already that the chromium is chromium 3. So the chromium has 3 positives. Now, it is attached to what? It is attached to 2 chlorides, and you should know that each chloride has 1 negative, so that means we have 2 negatives. The ethane, 1,2-diaminoethane, has no charge. It's a neutral molecule. So what the charges we have are 3 positives on the chromium and 2 negatives on the 2 chlorides. So my overall charge is +1. Do we understand this? Okay. Which transition metal complex is commonly used as treatment for cancer? You are required to know that this structure, which has platinum with 2 chlorides and 2 ammonia, this is called cisplatin. And it is cis because the 2 chlorines are on the same side. Platinum with 2 ammonia, 2 chlorine is called 2 chlorides is called platin. This is cisplatin, and it is the one used for treatment of cancer. If you look at the structure in D, the structure in D is transplatin. This is not the one used for cancer. It is the cis, in which the 2 chlorines are on the same side. Then this is cisplatin, used to treat cancer. Platinum forms a complex. Again, this is what we call platin, which is used in cancer treatment. 3 possible structures are these. So either you have the 2 chlorines on the same side and the 2 ammonias on the same side, or on opposite sides, or tetrahedral, as in Z. So which of these did we say was used for cancer treatment? Remember, it is the cis with 2 chlorines together, and the cisplatin is a planar structure, is a rectangular planar structure, not tetrahedral. So X is the structure of the cisplatin that is used in cancer treatment. The formula of 4 ions are shown. How many of these ions contain a metal with an oxidation number of +3? You should be able to calculate the oxidation number of the metal in each of these complexes. So if we have chromate, remember we said chromium, if I say the oxidation number of chromium is X, I don't know it. Each oxygen is -2, so that's -8. And I want the overall to be -2. That means the chromium is +6. Now in AlO2-, I don't know what the Al is. Actually, I should know it's +3, but anyway, let's calculate it. Each oxygen is -2. That means I have -4. So the aluminium has to be +3 so that I have an overall of -1. And so on. What about the third one? Fe with 6 cyanides. You should know that each cyanide has 1 negative. So that means I have 6 negatives. And the iron will have to be +2 in order to have an overall of -4. That last one, I have chromium with 2 chlorides, and you have to know that each chloride is -1, so that's a total of -2. Water has no charge. I want the overall charge to be +1. That means my chromium must be +3. So how many of them are +3? I have only 2 of them are +3. Okay, in the complex ion, the oxidation number of iron is what? Again, how do we calculate the oxidation number? The oxidation number of iron. Each cyanide has -1, so I have -6. I want the total to be -4, so the iron must be +2. In aqueous solution, iron 2 exists as complex ion. Explain how water acts as a ligand. We said, what is a ligand? A ligand is something that has lone pair of electrons to form a dative bond to the central ion. So how does water act as a ligand? It forms one dative bond, so that is why we call it monodentate, to the Fe2 plus in the middle using lone pair of electrons from the oxygen. Explain the shape of iron with 6 water. Iron with 6 water is octahedral. We have 6 dative bonds that need to be arranged for minimum repulsion between the 6 pairs of shared electrons. That means it has to be octahedral. Which complex has a ligand-metal ligand bond angle of 109? 109.5 means the structure is what? 109.5 means the structure is tetrahedral. So basically, we're being asked which of these has a tetrahedral structure. Well, in order to have a tetrahedral structure, we must have 4 bonds in the first place. So copper with 4 chloride ions, that is actually tetrahedral, and that is 109.5. What about the EDTA? We said the EDTA is a hexadentate. It forms 6 dative bonds, so this is how they are arranged. So it would be actually an octahedral structure. The silver with 2 ammonias, well, silver with 2 ammonias would be linear. Remember, I need the 2 shared pairs of electrons to be as far away from each other as possible for minimum repulsion. So this is a linear structure. And platinum with 2 chlorides and 2 ammonia, these are what we call square planar structure. Remember, platinum with 2 chlorides and 2 ammonia is not tetrahedral. It's square planar. Okay, platinum forms a complex with the formula this, and chromium forms a complex with this formula. What are the shapes of these complexes? So we said the cisplatin is square planar. Chromium with 4 chlorides bonded to it is tetrahedral. You have to know that. And if we ask why the 4 chlorines are tetrahedral, this is because the chloride ion is large and it needs to be as far away from each other as possible. What is the bonding between ligands and central atom in these complexes? So in these complexes, he's asking about what? He's asking about the bond between the ligand and the central atom. The ligand and the central atom, it is only dative covalent bond. What is the bonding within? Can you see the difference between the questions? The other one was saying between the ligand and the central ion, so we said only dative. What about within the complex? Now, what do we have within the complex? We have the water molecules have covalent, the ammonia molecules have covalent inside their molecule, and there is a dative bond between each of these and the central atom. So within the complex, I have covalent bonds and dative covalent bonds. Some nickel complex is formed by the addition of complexing agents to nickel 2 on formation. Which of these leads to the most positive increase in delta S system? I want to tell you that if you replace a ligand, a mono with a bidentate, or a bidentate with a hexadentate, the more ligands, the more dative bonds formed by the ligand, the more positive there is an increase in delta S system. So if I'm starting with nickel water 6, now I want to replace it by what? By 4 chlorides or by hexadentate ligand or bidentate ligand. Remember, if we replace it with a higher dentate, a higher number of dative bonds per ligand, this is more positive increase in delta S system. So if I replace a monodentate by EDTA, this is a more positive delta S system. Which complex ion is colorless? You should realize that transition metals, we said before, they form colored compounds. So if we have a choice between aluminium and iron and nickel and copper, of course the one that is not transition, so the aluminium for example, will not form a complex ion that is colored. So basically anything that is not a transition will form colorless compounds. Explain the shape of silver ammonia complex. We said silver is bonded to two ammonias. That means I have two bonding pairs of electrons. So this is linear, bond angle 180 for minimum repulsion between the two bonding pairs of electrons. Explain why silver ammonia 2 complex is colorless. Now, we just said transition metals should form colored, but silver plus forms colorless. This is because its 4D is complete. And you should know, why does a transition metal complex form colors, or why is it colored? This is because when the central metal ion forms dative bonds, this repels the d orbitals. This causes splitting in the d orbitals. Remember that at the beginning, all 5 d orbitals are what we call degenerate. They all have the same energy. The 5d orbital should have the same energy. But when the central atom forms dative bonds with ligands to form a complex, these d orbitals become non-degenerate. Non-degenerate means 2 of them get higher energy than the other 3. And that means when light goes through a solution like that, then electrons could gain an energy and jump to the higher energy level. And then the rest of the light that is passed through, this is the color that is seen. Do we understand how something is colored? If the complex metal ion now has incomplete d orbitals, so we must have incomplete d orbitals, then the electrons in the lower d orbitals can gain energy from the light and jump to the higher energy level, so the rest of the light is transmitted, and this is what we see. But what happens in the silver? Well, the silver plus ion has a completely filled d orbital. So no electrons can be excited to higher d orbitals. The electrons and the lower energy cannot jump to a higher energy level because it's completely filled. So no color is observed. All the light is passed through and we don't see a color. This question says diamine copper 1 ions are not colored. If we have copper 1, why would it not be colored? Because if we look at the electron distribution, copper is 29 and we said this is 4s1, 3d, 10. So if I'm trying to form copper 1 ion, I just remove the electron from the 4s. And that means the 3d sublevel is completely filled. And remember we said the complex is colored if the 3d is incomplete, so that the electrons in the lower d orbitals with lower energy would absorb energy, jump to the higher d sublevel or d orbitals, and the rest of the light will be transmitted. So if the 3d is complete, then the complex is not colored. This is because the d orbitals are fully occupied. Again, explain why oxyhemocyanin and oxyhemoglobin have different colors. If he's asking about any two compounds, we're not required to know what oxyhemocyanin looks like, but it is just a complex. And if we are asked why any two complexes have different colors, that would mean that the ligands are different. So energy difference between the d orbitals is different, and that means light of different frequencies would be absorbed, different light frequencies are transmitted, so different colors are observed. So this is the answer to why any two compounds do not have the same color. They will not have the same color if the ligands are different. That means the difference in energy between the d orbitals is different, and that means the electron, in order to jump to the higher d orbital, it would absorb different lights of different frequencies would be transmitted, different colors would be observed. Which ion is not blue? We are required to know colors of several complexes. You should know that VO2 plus is blue. This is vanadium in the +4 oxidation state. It is blue. Cobalt in water, this is not blue. This is pink. Chromium in water forms a blue solution. Copper in water forms a blue solution. So the one that is not blue out of all of this is the cobalt complex with water. Cobalt chloride is used as a test for the presence of water. Remember, we said cobalt chloride complexes or compounds of cobalt have different colors, and we used this as a test for water. So we said, what is the test for water? We add anhydrous cobalt chloride. It turns from blue to pink. Which equation shows a redox reaction in which the solution turns yellow? You are required to know some of these colors. For example, we are required to know that iron 2 compounds are green. The VO2 plus is yellow, but is this reaction a redox? When we have acid plus base to give salt plus water, this is actually neutralization, not a redox, but the VO2 plus that is formed is yellow. Now, dichromate to chromate, you should know that the dichromate is orange, and when it forms chromate, the chromate is yellow. So, dichromate, or the dichromate is orange. The chromium water complex is green. Now, when we react chromium water complex with hydrogen peroxide is an oxidizing agent. It converts the chromium 3 plus to chromate ion, which is yellow. So this is a redox reaction. Aqueous ammonia is added in excess to aqueous solution of copper 2 plus. Okay. We should know that copper 2 plus, when we dissolve it in water, it forms the copper 6 water complex. So we are starting anyway with a solution of copper 2 plus. That means we're starting with copper water 6 complex. Now you should know that when I add a small amount of ammonia, we get a blue precipitate. This is the copper hydroxide. But if we add excess ammonia, then we form the copper ammonia water complex, 4 ammonia, 2 water complexes, and that is a dark blue solution. So you should realize that this is the equation when we add excess ammonia to copper solution, copper 2 plus solution. Which metal hydroxide precipitate is soluble in both excess aqueous ammonia and excess sodium hydroxide. Remember we did before in qualitative analysis in tests for ions, we did tests for copper 2, iron 2, we did tests for zinc 2+, and if you remember zinc 2+, if you add excess ammonia or excess sodium hydroxide, at the beginning you get a white precipitate, and then in both cases it will dissolve to form a colorless solution. So this is the precipitate that will be soluble in both excess ammonia and excess sodium hydroxide. Again, a small amount of aqueous ammonia is added to aqueous solution containing zinc. So I'm starting with zinc with 6 water, zinc ions in solution. Now I'm going to add what? In this case, he's saying I want to add a small amount. So we said if we add drops of ammonia at the beginning, we get a white precipitate. Which of these is the one that forms a white precipitate? First of all, if we say we're looking for a precipitate, that means we should not form something that is charged. A precipitate is a complete compound, not a complex ion with a charge. So A and C are wrong. The products here will not be precipitate. So we're looking for B and D. And of course, if he says, I am adding what in this case? I'm adding small amount, then it is the less amount of ammonia that you're adding to give the white precipitate, which is involving zinc hydroxide, or in water we write it as zinc hydroxide with 4 water. When aqueous ammonia is added to an aqueous solution of zinc sulfate, so again this is zinc 2+, a white precipitate forms which dissolves in excess ammonia to give a colorless solution. What type of reaction is all of this? Remember, if I have zinc in solution, so that is zinc with 6 water complex, I'm adding a small amount of ammonia, so that is 2 ammonia. This gives me the precipitate, which is zinc hydroxide with 4 water. This is a deprotonation reaction. The first part is a deprotonation reaction, and then when we add excess ammonia, we are replacing water with ammonia. This is called a ligand exchange or ligand substitution. So first, when we are changing water into OH-, that means we're removing an H+ from the water. That is deprotonation. And then when we add excess ammonia and replace some of the water ligands with ammonia, then this is ligand exchange. Cobalt 2 oxide is used in ceramics industry as an additive to produce blue glazes and enamels. Cobalt 2 oxide dissolves in sulfuric acid to give a pink solution of cobalt 2 sulfate. When concentrated hydrochloric acid is added to aqueous cobalt 2 sulfate, a dark blue solution forms. Name the type of reaction that occurs when concentrated hydrochloric acid is added to cobalt 2. Remember, this is a type of ligand exchange where we're changing the water ligands with chloride ligands. Write an ionic equation. So what are we doing? We are starting with cobalt solution, cobalt sulfate or cobalt anything. An aqueous solution means the central atom, the cobalt, the metal ion, will form complexes with water. So we start with cobalt water 6 complex. Then we're adding chloride and we're exchanging the water with chloride ion. So this is called ligand exchange. And of course you need to balance this equation. Explain why the shape of the complex ion changes when concentrated hydrochloric acid is added. Again, we said if I have cobalt with 6 water, then this is octahedral. But when I react it with the chloride, it forms 4 chloride ions, 4 dative bonds with 4 chloride ions. This is tetrahedral. Now, why is it tetrahedral? So the cobalt water complex is octahedral. But when I react it with HCl, the cobalt Cl4 complex is formed, and that is tetrahedral. This is because chloride ions are large and only 4 can coordinate around the cobalt 2 ion. Now, this is a type of question that usually has about 6 marks. And here you're required to compare and contrast the reactions in aqueous solution of nickel 2 sulfate with sodium hydroxide and with ammonia. So we need to mention what would be seen, the equation, and the type of reaction. So we're starting with nickel 2 sulfate solution. That means I have nickel 2 in solution. So the first thing that happens is it forms a complex with 6 water, and you have to remember the colors. Nickel complex with 6 water, this is nickel 2 plus with 6 water, this is green in color. And then what are we adding? We're adding sodium hydroxide or ammonia. When we add sodium hydroxide or ammonia at the beginning, we have what we call deprotonation. Deprotonation means the H of 2 of the waters is removed, and this forms a gray-green precipitate of nickel complex with 4 water and 2 hydroxides. So this is the first thing that happens when we add either ammonia or hydroxide, sodium hydroxide. And then what? And then on adding excess ammonia, there is ligand exchange. On adding excess ammonia, the water ligands are exchanged with ammonia ligands, and this forms a blue solution. Remember, the nickel 2 plus with 6 ammonia is a blue solution. With the hydroxide, nothing changes. The gray-green precipitate remains. Another question like this: describe the reactions of samples of cobalt 2 sulfate with aqueous sodium hydroxide and aqueous ammonia and concentrated hydrochloric acid. Okay, so we're starting again with cobalt 2 plus in water. This forms copper water 6 complex, and this is pink in color. You have to remember that the cobalt with 6 water around it in a complex, this is pink in color. And then when we add sodium hydroxide, this forms a blue precipitate. This is where we have 2 of the waters are deprotonated to form hydroxide ions. So this is deprotonation reaction. And then we're adding aqueous ammonia. Well, when we add ammonia, it forms a brown solution of cobalt with 6 water complex. If we add concentrated HCl, remember you're required to know these equations, so you should know the equations and the colors and the structure of the complex. So cobalt reacts with the chloride to form cobalt 4 chloride ligands, and this is a blue solution. Remember, when we replace the water with chloride, this is called ligand exchange or ligand substitution reaction. Aqueous ammonia is added drop by drop to a solution of cobalt 2 chloride. What would be the sequence of observations? Again, what did we say? We said cobalt in water is pink. Cobalt complex with water is pink. When we add what? We're adding hydroxide, whether it's aqueous ammonia or sodium hydroxide, it forms a blue precipitate. So there is deprotonation of 2 of the water molecules to change them to hydroxide. Then we have a ligand exchange in which ammonia replaces the water molecules. This is a brown solution or a yellow-brown solution. Aqueous sodium hydroxide is added to iron 2. Again, what is the color of iron 2 complex in water? This is green. So we're starting with a green solution. Now we're adding what? Sodium hydroxide. This gives a green precipitate. But then he's saying it is allowed to stand in air. Remember, this green precipitate is due to iron 2+. But if I leave it in air, it is oxidized to iron 3+. So the green precipitate turns brown. Iron 2+ forms a green precipitate. If left exposed to the air, it is oxidized by oxygen in the air to form a brown precipitate of iron 3+. A series of reactions with iron and iron complexes was carried out. I have a sample of iron was heated with hydrochloric acid, and a pale green hydrated salt A with molar mass 198.8 was crystallized from the solution. And the first question says, deduce the formula of the hydrated salt A. I started with iron. I heated it with hydrochloric acid. That means my compound is iron 2 chloride. Now, iron 2 chloride with a certain amount of water, because it says hydrated salt. The total MR we're given is 188.8. So I can use that to determine how much water we have. And that means you can solve for the X, and this comes out to be 4. So we find out that the formula is actually FeCl2 for water. Remember, how did we know that it is iron 2 chloride and not iron 3 chloride? The question says a sample of iron was heated with hydrochloric acid and a pale green salt. Green means it's iron 2, not iron 3. So we have FeCl2, and then we calculate how much water. It comes out to FeCl2 for water. Then the next part of the question says this salt A, which we decided is iron 2 chloride, was dissolved in water, forming a pale green solution containing a complex iron B. Okay, if we have iron 2 chloride, I dissolve it in water, I end up with the iron 2 complex to 6 water. This is what we form when we dissolve the metal ion in water. So it's FeH2O6, and this is iron 2, so the overall charge on the complex is 2+, since each water does not have charge. Then the question says, on addition of excess aqueous potassium cyanide, the solution turned yellow due to the formation of complex ion C. So complex ion C must be a complex between cyanides and the iron 2. Remember that the iron central atom has a charge of +2. Each cyanide has one negative charge. So 6 negatives plus 2, I have a net charge on the complex of 4 negatives. And of course, if you have 6 of them bonded to the central metal ion, then this forms an octahedral structure. Again, remember, this is a 3-dimensional structure in which the thick black bond indicates that the cyanides are coming out towards us. The dotted bonds indicate that these cyanides are towards the back of the diagram, and that shows the 3-dimensional structure or the 3-dimensional shape of the complex. Iodide ions are oxidized to iodine by these types of ions. Iron 2 acts as a homogeneous catalyst, part of the syllabus requires that you know the meaning of homogeneous and heterogeneous catalyst. First of all, state why the catalyst here is described as homogeneous. Remember, we have two types of catalysts. Homogeneous catalyst is when the catalyst and the reactants are the same phase or the same state. So all of them are solutions, or all of them are the same state. Heterogeneous means the catalyst is a different state from the reactant. So the reactants could be solutions, but the catalyst is a solid, for example. Now, here what do we have? We have a solution of iodide with a solution of the peroxo disulfate ions, and we have iron 2 solution. So all of them are solutions. The iron 2 is regarded as a homogeneous catalyst because the catalyst is in the same state as the reactants, since all of them are in aqueous solution. Write two equations to show how iron 2 ions catalyze this oxidation reaction. Remember, you are required to know that this kind of reaction requires iron 2 plus and iron 3 plus to act as catalysts, because the iron 2 plus reacts with this first reactant to form iron 3 plus, and then the iron 3 plus reacts with the other reactant, which is the iodide, to form iron 2 plus. So in that case, the iron 2 plus has been used and then regenerated, so it acts as a catalyst. So just how iron 2 ions lower the activation energy of this reaction. Remember, we said if it acts as a catalyst, then it lowers the activation energy. Why are we saying it lowers the activation energy? This was the equation we were talking about. And you can see that the reactants are both negatively charged. So I'm trying to react a negatively charged species with another negatively charged species. They will repel. The two reactants are negatively charged. They repel. And so when the ion reacts, this involves the reaction of oppositely charged ions. So the activation energy is lower. Iodide ions are oxidized. Again, this is the same equation. We are required to know this equation. Which of the following statements is true of this reaction? Well, we already know that for this kind of reaction, I need iron 2 plus and iron 3 plus to catalyze the reaction. Again, the same equation, and the question is, this reaction is catalyzed by adding iron 2 plus. This catalysis is effective because what? Why is it that the iron 2 plus can act as a catalyst here? We said what happens? The iron 2 plus is oxidized to iron 3 plus, and then the iron 3 plus is reduced back to iron 2 plus. So it acts as a catalyst effectively because the iron 2 plus is readily oxidized to iron 3 plus, and then it is reduced again, so the iron 2 plus is regenerated. The reaction of, this is another reaction that you should be aware of. This manganate with the ethane diowate ion forms manganese 2 plus, carbon dioxide and water. This is an example of autocatalysis. Autocatalysis means one of the products that is formed from the reaction acts as a catalyst. So you should remember that this is an example of autocatalysis because the manganese 2 plus that is formed acts as a catalyst. So at the beginning, the reaction is very slow. But as soon as it starts to form manganese 2 plus, the presence of the manganese 2 plus helps to catalyze the reaction, and the reaction becomes faster. The sequence shown is the mechanism for a reaction in aqueous solution. So if we're given a sequence like this, in the overall reaction, which of these would be correct? Well, let's look at the equations. You can see that what I have is the Ag plus forms Ag2 plus, and then the titanium plus reacts with the Ag2 plus to form Ag plus, and the titanium 2 plus that is formed will react with the cerium. So in the overall reaction, The silver plus that reacted at the beginning was regenerated in step 2. So actually this is catalyzed by the Ag plus ions. Remember, if something reacts in step 1 and then it's regenerated again, then it is a catalyst. Which substance is manufactured in a process involving a reaction catalyzed by vanadium oxide? You are required to know these examples of reactions that have catalysts which are transition metals. Ammonia is formed by what we call the Haber process, nitrogen plus hydrogen to form ammonia. This is a reaction that uses iron as a catalyst. He's asking, where do we use vanadium oxide? So please remember, to make ammonia we use Haber process, and this involves iron catalyst, not vanadium oxide. To make nitric acid, this is a reaction that does not involve a catalyst from transition metal at all. It's actually a reaction to form nitric acid by reaction of potassium nitrate and concentrate sulfuric acid. So this doesn't have the catalyst we're looking for. To make sodium hydroxide, again, remember the sodium hydroxide is made by electrolysis of sodium chloride solution. This does not involve a catalyst. But what about to make sulfuric acid? To make sulfuric acid, we do a process called contact process. The contact process involves reaction of sulfur dioxide with oxygen to form sulfur trioxide, and then the sulfur trioxide is used to manufacture sulfuric acid. Now, this contact process, reaction of sulfur dioxide with oxygen to give sulfur trioxide, uses vanadium 5 oxide. So this is the one we are looking for. The catalyst here is V2O5. Compare and contrast the mechanism of the action of platinum as a catalyst in the removal of pollutants from car engine exhaust fumes with that of vanadium oxide as a catalyst in the contact process for manufacture of sulfuric acid. Please pay attention to this. We said we can use platinum as a catalyst in the catalytic converter. Remember, both platinum and V2O5 are acting here as heterogeneous catalysts. But the difference is, in the catalytic converter, what is the catalytic converter? This is something that is placed in the car exhaust, and it is used to remove the harmful gases so that they do not affect the environment. So what happens in this case is the reactants, which are the harmful gases like carbon monoxide and nitrogen monoxide, are adsorbed on the surface of the catalyst. And we said the catalyst is usually platinum. So the reactants are adsorbed on the surface of the catalyst. This weakens the bonds in the reactants and helps the reaction to occur quickly. Then the products are removed from the surface, so we say there is desorption of the products. So the reactants are adsorbed on the surface of the catalyst, then the products are desorbed or removed or escape from the surface of the catalyst. Remember that in the catalytic converter, we have mainly reaction of carbon monoxide plus nitrogen monoxide, which are harmful gases, to give carbon dioxide plus nitrogen, which are already present in air. We also have reactions of hydrocarbons with some of the gases to give things like carbon dioxide, water, and nitrogen. So this is what happens in the catalytic converter. But in the contact process, we use V2O5. So again, we have gases and the catalyst is a solid, so this is heterogeneous, but this acts in a different way. The V2O5 reacts with one of the reactants, which is SO2. So the V2O5 is reduced by the sulfur dioxide to form V2O4, and then the V2O4 is oxidized by the oxygen to regenerate the V2O5. So this is what happens in the contact process. Hemoglobin. Hemoglobin is another example of a complex It is an iron 2 complex, and this makes dative bonds with oxygen. So the oxygen attaches to the hemoglobin to form oxyhemoglobin. This forms dative bonds. The oxygen molecule forms dative bonds with the central iron 2 plus. The 4 nitrogen atoms are part of a multi-dentate ligand in the heme group. Explain in terms of iron 2 why carbon monoxide is toxic. Hemoglobin carries oxygen to body cells. The oxygen forms dative bond with iron 2 plus. But if there is carbon monoxide in the blood, then it is the carbon monoxide that forms a dative bond with the iron 2 plus in the hemoglobin. This forms carboxyhemoglobin. So the carbon monoxide replaces the oxygen, and the problem is the dative bond formed by the carbon monoxide is stronger than that for the oxygen. So once the carbon monoxide forms a dative bond to the iron 2, this binds very strongly and it forms a stable complex. So basically the hemoglobin cannot transfer oxygen anymore, and this is toxic to the body. When oxygen binds to the heme group in hemoglobin, each oxygen molecule does what? We said when the oxygen binds to hemoglobin, it bonds reversibly. It forms a dative bond, but then this dative bond can be broken to give the oxygen to the body cells. This is the end of this for now. I hope this was useful to you and this made the chapter a little bit easier. Thank you for listening.